Okay, so coming back to working with growth and decay by a percent, let's read this example. As water drains out of a pool, the depth of the water decreases at a constant percent rate of 20% per hour. All right, so guys, remember the key is anything that grows or decays by a percent is multiplicative, because anytime we do percentage of something, we multiply. Therefore, this is why we're going to create an exponential function. The depth of the water when the draining begins is 12 feet. Anytime we're creating any exponential function, we need two things. We need to know what was the initial value and what was the multiplier. So in this case, if we want to write a function that would describe the depth of the water of the pool as the function of time remaining in hours as it's drained, we could call this function d of t equals, remember we always put our initial value first, so we would say 12 times, and then we need our multiplier. Well, anytime something grows or decays by a percent, you have to start with 100%. So if we have 100%, but it's decreasing by 20% each hour, that means we're losing 20% of its value each hour. So what we keep is 80%. The multiplier always has to be changed to be a decimal, So to change percentage to a decimal, we divide it by 100, or we move the decimal place 2 places to the left. And when we do that, we get our multiplier as 0.80. Another way you can look at it is you can start by changing the 20% to a decimal. So we would move that 20% decimal place over 2 places to the left, which would make the rate 0.2. Then you can subtract it from 1. Remember, anytime we're doing something that is a percent decay problem, to get the base we say 1 minus r, where r is in that decimal form. So we then say 1 minus 0.20, which is the same thing as 0.8. So there's two ways to do it. You can either think of it as a percentage and then move the decimal, or go ahead and move the decimal and then subtract it from 1, or in the growth case, add it to 1. And so we get the base here is 0.8 or 0.80 raised to the t. All right, so this is what we learned yesterday. But today, we want to be able to answer questions about it. So what if we had a question like this? It's safe to cover the pool after it reaches a depth of 1 foot or less. What is the minimum number of whole hours that we should wait to cover the pool? Explain how you found your answer. One way we could do this problem is we could go to Desmos, type our function in, y equals 12 times 0.80 raised to the x. It would graph our function, and remember you can always kind of click in and pull down, then you can really see what's happening where that initial value was at 12 when we have 0 hours, and then it is decaying by 20 or losing 20% of the depth of water each hour. We could then change this into a table by duplicating and then making this a table. Now, of course, these negatives really don't make sense in the context of the problem. If we talked about the domain in the context of the problem here, the domain would only be from 0 hours and greater. We wouldn't have less than 0 hours because that just doesn't make sense. But we could come down here and keep pressing enter. And remember, it wants to have less than 1 foot of water. So we can see that in order for it to be less than 1 foot of water, it would take a minimum of 12 whole hours to cover the pool. Another way you could do it is you could come in here and you could intersect this function with the line y equals 1, and then come over and hover at where that's at. And we can see that it took 11.136 hours for it to reach a depth of 1 foot. But we want it to be less than 1 foot, and it has to be whole hours. So we wouldn't round down in this case, or we wouldn't be less than 1 foot. We would have to round up and make it 12 hours. We can also do these things in our graphing calculator for those of you who have a graphing calculator at home. You would just go to y equals, type in your function, and then hit second graph, which is our table, and scroll down in your table to see how long would it take for it to reach less than 1 foot, and we can see that would be 12. You could also do it graphically. Okay, let's return back to the problem at the end of our lesson yesterday. If a city is with a population of 50,000 is decreasing at a rate of 1.16% each year, write a function that models the city's population over t years. And then we found what would the population be at 10 years and at 50 years. What if it asked how many years will it take to have a population of approximately 20,000? Again, you could use Desmos or your graphing calculator to figure this out. You're not going to solve this algebraically until you learn get into Math 3. So what we could do is go into Desmos, type in our function, and then we would type in our second place and put y equals 20,000, because what we want to try to do is figure out when these intersect. This is why learning systems of equations back in Unit 3 is so important, because we use it not just for lines, but for all kinds of functions. So we graph both of these, and we come over here where we can see they're intersecting, and we hover on the intersection. And what we can see is it gives us 78.532. So if the question said how many years to the nearest year, you would say 79 years. If it says to the nearest tenth of a year, you would say 78.5 years. And so you just have to look at how the question's asking you to answer it. Okay, let's check out a problem like this. Town A adds 10 people per year to its population, and Town B grows by 10% each year. In 2006, each town has 145 residents. For each town, determine whether the population growth is linear or exponential. All right, so this is one of the things that's really important, guys, is that we can figure out the difference between a linear function and an exponential function. In the first case, it adds 10 people per year. That is a constant rate of change, so that one would be linear. Where in the second case, it's growing by 10% each year. Anything that grows or decays by a percent is exponential. So this case would be exponential. All right, so the important part is that they both have the same initial value. They both start with 145 people, but the way they grow changes. So for Town A, because they add 10 people every 1 year, that gives us our slope. And then our y-intercept would be 145. So the equation will be y equals 145 plus 10x. Or you could say 10x plus 145. For Town B, because it grows by 10% each year, remember that the multiplier would not be 0.10. It would be 1.10. You can't forget that you have to add that 10% to 100%. So it's 100% plus 10%, which is 110%. And then you've got to change it to a decimal by dividing by 100 or moving that decimal place over 2 places to the left. So the multiplier is 1.10, not just 0.10. And of course, we would write this as an exponential function where we have our initial value, 145, our multiplier, and then raised to the x. Okay, I would like for you just to read each one of these scenarios and decide whether it is a linear relationship or an exponential relationship. You can just take a little sheet of paper and jot it down. Just put E or L and why you think it would be, because that's something that's really important for us to pick out. Pause the video, go ahead and do it, and then start the video back. All right, so folks, the first one would have been linear because it is just a deposit of $723 per month and there is no interest earned. The next one's exponential because it depreciates. Remember, depreciates means to decrease in value by 17% per year. As soon as that percentage came in there, that made that exponential. Folks, remember, if you had to actually write a problem about this, the multiplier would end up being 0.83. You would have to say 100% minus 17%, which is 83%, and then change it to a decimal. The next one's exponential because you're doing 9/10 of that substance each week, and that is multiplicative. D is linear. It subtracts 1 liter each day. And E is exponential. It is a halving behavior, and halving is multiplicative. Okay, let's look at these two problems. What I would like for you to do is I would like for you to try both of them. Just pause the video, just read them and try them, and then when you're done, turn the video back on. All right, so the first problem says the Greens bought a condominium for $110,000 in 2000. If the value appreciates at an average rate of 3% per year, what will the value be in 2015? And remember, appreciates means to increase in value. Okay, so the initial value here is $110,000. The rate it's growing at is 3% per year, so 3 divided by 100 is 0.03. and the time that has elapsed is 15 years. Anytime you have a problem that throws years at you, all you have to do is subtract the 2 years to find out how much time has elapsed. So if we do it using the formula, we would say our initial value, 110,000, and then because this is appreciating and it's percent growth, you do 1 plus the rate, so that's 1.03, and then we raise it to the 15th power. You can also figure out this multiplier here by just thinking about it as 100% plus 3% is 103%. Then move the decimal over 2 places to the left to change it from a percent to a decimal so we can multiply. Again, remember folks, the 1 holds the value there, and then the 0.03 adds that 3% each year as it grows. And that would be our answer. And you can use Desmos or your graphing calculator to get it. All right, let's check out the next one. During the 1990s, the forested area of Guatemala decreased by an average rate of 1.7%. If the forested area in Guatemala in 1990 was about 34,400 square kilometers, write an equation for the forested area for T years after 1990. And then if this trend continues, predict the forested area in 2015. All right, so the key to this problem is that it is decreasing. And it is decreasing by a percent. So again, it is an exponential problem. You can use the decaying formula, y equals a times 1 minus r to the t. If you do that, you need to change your 1.7% to a decimal first. So that's 0.017. So then when you set that part up, you would say 1 minus 0.017, which gives you that multiplier of 0.983. The initial value is 34,400. Or to get that multiplier again, you can say 100% minus 1.7%, which is 98.3%, and then divide this percent by 100 or move that decimal 2 places to the left, which gives you 0.983. Because 25 years have elapsed, we would then raise it to the 25th power, put that in, and it gives us approximately 22,407.7 square kilometers of forested areas left 25 years later. Last but not least, we're going to have a couple of problems where you have to pick out the correct function. So it says, which of the following equations would model an exponential quantity that begins at a level of 16 and decreases at a constant rate of 8% per hour? All right, so guys, one of the things I want y'all to pay attention to is look at answer choice D. In answer choice D, the base here is -7. That's not even possible. Your base always has to be a positive number. Also, it says that it's decreasing at a constant rate. So anytime it's decreasing, that multiplier should be a number between 0 and 1. So look right here in answer choice C. That is 1.018. That is not decreasing. That would be increasing at 8%. So that would be incorrect. So we're down to the top two, A and B. They both have the correct multiplier, 0.92. If you say 100% minus 8%, what remains is 92%, so the multiplier would be 0.92. However, A would be the correct answer because it is in the correct form. B is incorrect. We do not add 16 to the multiplier raised to the power. All right, so you're going to do a little Google form assignment today. So it's going to have questions. Most of them are multiple choice. You can use paper and Desmos to work them out, or your graphing calculator. And then you will pick the multiple choice answer, and there may be 1 or 2 that are type in. Just go along with it. Tomorrow we're going to review all of our exponential function problems, even exponent rules, and then Thursday take a little assessment. Good luck, and see you tomorrow.